Now we'll study phase propagation on simple harmonic waves on a string. You must always keep in mind that in a simple harmonic wave, along with energy, phase also propagate with same speed. Here many students might confuse what do you mean by phase propagation. So to understand this phase propagation, let's discuss microscopically how the waves are generated in a string. Say we are given with a stretched string, and at one end of the string we are having an oscillator which is oscillating in a perpendicular direction with amplitude A in a simple harmonic motion, and say it starts at t equal to 0. Now say if it will start moving up. I just draw step-by-step pictures of the string as the particle completes its oscillations. Say it is going up. So if it is moving up in the upper half of its cycle, the string will take a shape like this, and along with its movement in upward direction, all medium particles are lifted in upward direction, or we can say these particles will gain velocity and momentum in upward direction because these are all connected to each other. Now when it will reach the top and return, what kind of situation will be there? Let's draw it. Say we assume the particle has reached this upper extreme position and then it is coming back and it is at this position. So it will be coming down. The shape of a string would be like this. As it is coming down, it is pulling the particles in downward direction. This particle will be at its upper extreme, and due to momentum in these particles, these all are still going in upward direction. Because we can say this particle which is just starting its oscillation, it is due to the influence of its previous particle. So the previous particle is lifting the next particle in upward direction. So it will gain momentum upward. So here also it is happening. When this oscillator particle will move at the extreme position and it will return, this will come to rest, and at the next moment next particle will come to rest. Similarly, this will take such a shape. Let's consider what will happen if particle will complete half oscillation. If oscillator particle will complete its half oscillation, it will create a wave pulse which is just in the upper half of the wave. So in this situation, still the particles which are connected to the oscillator are moving in downward direction, and as every particle is having a tendency to move upward, in the right half of the pulse, these all are lifting string particles in upward direction. Now in this situation, I can say if after half oscillation the oscillator is stopped, this pulse will carry on as it is, as these all particles will be raising the next portion of string in upward direction, and these all will start coming to rest. So this pulse will continue. Now if it completes the lower half of oscillation, we can say that another downward pulse is created, and the upward pulse, this will travel to this position. In this situation, all these particles are moving in downward direction. All these particles are going in upward direction, and as the particle is now moving up at the oscillator, it is bringing all the particles together. Now in this situation, a complete wave train, a single wave train is generated. Now if the particle at the oscillator will stop, this single wave train which is composed of one upper pulse and one lower pulse will continue to move with the wave speed v, which is decided by the properties of a string. Now if this oscillator particle will continue to oscillate, similar wave pulses, alternate wave pulses upward and downward are generated, and a continuous wave train is produced. Now this is the distance traveled by the wave during one complete oscillation, which we term as wavelength of the wave, denoted by lambda, which is written as Vt. We already discussed in the previous section. As we have just now discussed that in a string, at one end if an oscillator oscillates simple harmonically, it produces a wave train like this, And in this situation, we can state the wave is continuously moving forward with the speed v. So at t equals to 0, if the oscillator starts between amplitudes plus a and minus a, the wave is generated and travels at a speed v. So at time t, if wave reaches a point P, we can say that point P will start oscillating at time t. That means it will start at time t in a phase exactly at which the oscillator started at t equal to 0. So if this point is at a distance x from the origin, we can simply write x is equals to Vt. That means the phase in which the P is starting its oscillation, it was the same which was exactly Vt distance behind the point P at oscillator, which was at time t equal to 0. That means at time t, the phase of particle is also propagating at the same speed v, because the particle which is ahead of any point will acquire same phase as that of its previous particle within the given time duration. Like for example, we consider 2 points A and B which are oscillating up and down at these positions, and they are situated at a separation delta. Here we can say point B will start oscillation after a time delta by V when particle A is started. If the separation is delta, say at time t1 particle A is started its oscillation, then at time t1 plus delta by V, B will start its oscillations. That means the phase difference between SHMs of A and B is, this phase difference can be written as omega into delta by V, because omega is the angular frequency of SHM and delta by V is the time lag between the two. So this can be written as omega, we can write as 2 pi into frequency multiplied by delta upon speed of wave, can be written as n lambda. In this situation n gets cancelled out. This is written as phase difference is equals to 2 pi by lambda into delta. Here 2 pi by lambda can be written as k, where k is called angular wave number for a simple harmonic wave, where the value of k is 2 pi by lambda. You should always remember, whenever we need to calculate phase difference between any 2 points in a simple harmonic wave, it is given by 2 pi by lambda multiplied by the path difference of the two particles. This is quite a useful relation in analytics of a simple harmonic wave, and we are going to use this expression several times in the sections later. So be careful. Phase propagation implies whenever a particle is oscillating in a specific phase at a distance delta, the particle will acquire same phase after time delta by V, or we can say the phase is also propagating at the same speed with which the energy is flowing in the wave. Or we can conclude or summarize the whole situation in a way that every particle in a wave acquires the phase of its previous particle as the wave propagates.